Okay, good evening, everybody. Today's lecture is on causality. It's a topic in the area of probabilistic graphical models, where the goal is to construct Bayesian networks where the network connections are causal. A normal Bayesian network does not have to be causal. It is directed arrows. You can construct it in whatever way you want. And of course, that will build in certain independences into it. And so you are able to represent a joint probability distribution. Here, we are interested in a causal Bayesian network. So the topic of causality is of great interest to robust artificial intelligence. And we'll see why that is the case and why intelligent systems need to have some understanding of causality in addition to correlations. The power of deep learning networks is to understand that correlations exist in the data. That is how deep networks are able to converse in language, for example, give sounding sensible answers because it is exploiting the correlations that exist in the data. If there is this word, then the next word ought to be this other word. That's a correlation. And so we argue here that a probabilistic model simply based on correlations is insufficient to exhibit the kind of intelligence human beings do, and causality is an essential part of that. Okay, so we will cover these topics. And how does one discover causality? It's a very challenging issue, and we will see what inroads have been made and how they could come into play eventually into a machine learning system. All right, I'm going to now share the slides of this lecture. Okay, here we are. Okay, the topic is causality. And the topics we will cover is really a broad-based coverage of the whole topic of causality. One can argue, well, isn't this more about artificial intelligence? Yes, but causality is a big, broad issue. So I think we need to have an appreciation of it. And some of these causality issues are difficult for human beings also to deal with. But anyway, we are interested in constructing machines maybe as good as humans or even better than humans. So why not study what does it take to program causality? All right, so we'll begin with the importance of causality in science. And then we'll talk about the importance of causality in machine learning. And we will make a distinction between probabilistic models and causal models. Probabilistic models may show some directed edges between variables, indicating some kind of correlation that exists between these variables. But how can we make sure that they're causal? And so that involves essentially a discussion of correlation versus causality. We'll look at some examples of that. And then we introduce a concept called interventions. So this is, if you have a model of the world with all the variables, how do we intervene to discover whether it is correlation that we have or whether it's causality that we have between variables, all right? Causality means A causes B, right? And not B causes A. That would be the opposite of causality. And correlation means just A and B are correlated, right? So, and then we'll look at what does it take to identify causality. Okay, so the causality is a relationship between an event, the cause, and a second event, the effect, where the second is understood to be a consequence of the first. The examples are things like rain causes mud, not mud causes rain, or rain causes umbrella to be opened, not that when you open an umbrella, it's going to rain. A deep learning network could very well assume that when you open an umbrella, it will start raining because there's a correlation between the two. We want that system to be knowledgeable enough to know that it's only one way. Rain causes umbrella to be opened, not the other way around. Then there are issues. We look at this issue of smoking causes cancer. There's been an argument on this issue, whether it's really cancer causes smoking or certain genotypes influence both smoking and cancer. So those are interesting issues. Altitude lowers temperature and so on. One can come up with many examples. Causality is an important topic in philosophy and science. Democritus of 460 to 370 BC, father of modern science, said, I'd rather discover one causal law than gain the kingdom of Persia. He wanted to understand the world, that A causes B, that gravity causes things to fall off the tree. Karma in Indian philosophy, or Sanatana Dharma, a person's actions causes certain effects in current and future life, either positively or negatively. So that involves a slightly non-scientific assumption about people having future lives. And but the karma philosophy says that your actions cause effects not only in your current life, but also future life. So anyway, these are all, causality is kind of something that people have thought about deeply. Causality in medicine is a medical treatment, possible effects of a medicine, because the right treatment saves lives. Is this the medicine that's curing people? Is taking the Moderna vaccine is what is preventing COVID-19? Another example is vitamin D and arthritis. People who took vitamin D seem to have less arthritis. But that turned out to be correlation rather than causation, because those who took vitamin D were also exercising. And the cause of arthritis decreasing was exercise, not vitamin D. So vitamin D and arthritis are correlated, whereas exercise and arthritis are a causational aspect. All right, so this I already mentioned, vaccination and COVID-19. Newspaper report there's a correlation between Pfizer vaccine and fewer COVID deaths. Is that causation or correlation? And correlation may be due to unrelated facts, such as those countries have a younger population, have a higher average temperature. So we need to kind of eliminate some of these what are called latent variables to see whether there's really causation. So it's important to know whether causation exists before we take a medicine, right? So we just don't want correlation. And what is the normal way of checking for causality? Would be a random correlation test for causality between Johnson & Johnson vaccine and lower incidence of COVID-19. They set up two groups with and without vaccination, making sure that there are no other intervening hidden variables such as age, temperature, or country. So there are two populations, the blues and the greens, and then expose both groups to COVID-19. These people went about their work, and they found that the placebo group, which did not have any vaccination, they contracted 63 per 5,000 volunteers, as opposed to the vaccinated group, about 18 per 5,000, which reduces, if you take that as a percentage, 18 as a percentage is 63, 72%, is less risk by taking the vaccination. So that's a randomized correlation test. But we are now talking about just in general observational data, not setting up a particular test. So determining causal relationship, best way is randomized controlled experiments may be too difficult or immoral to perform. For example, you cannot ask a bunch of people to go smoke and come back and see whether they got cancer or not, right? So you may not be able to do that, and you want to be observing data and then inferring whether there is causation. Want to rely on observational data to infer causal relationship. So this is just like in deep learning. We observe a lot of data and then we decide there is correlation between these. And so we are able to build a system for generating natural language text like Alexa and so on, based on the correlations that exist in the data. Can we do that for causality? Current statistical methods are good at determining correlation. So we are able to detect correlation between data. This is done by having lots and lots of data available. And we go about looking at the statistics. That's what all the probabilistic models, starting from logistic regression all the way to multi-layer neural networks and so on, they are able to observe the correlations that exist between features and so on to be able to make a prediction, for example. Correlation only hints at causality, but is not causality directly. So what is the role of causality in machine learning? We can look at the big picture and say, what are the shortcomings of machine learning? Transferability to other distributions is one of them. So refer to domain adaptation, or sometimes we refer to lifelong learning. Human beings are able to do that. So in a sense, can we go out of the distribution in which the data has been presented to different distributions and still perform well? That's the transferability issue. The second one is explainability of predictions. So that is a second issue is rather than work with latent variables that are computed by the network, can we have some explainable type of latent variables that are constructed? And a third shortcoming of machine learning are lack of understanding of cause-effect relationship. And this is a hallmark of human cognition. Human cognition, I'll show you some more examples why it is a hallmark of human cognition. Even very simple things we observe, we are building causation into it, not correlation only. And by understanding the cause-effect relationship, we can allow interrogating a parsimonious representation. The representation can be more condensed if we know that it's a cause-effect relationship. And causality will enable machine learning without much training. So there are all kinds of promises that if you're able to understand causality, you can do with less training and so on. Here is a diagram I came across where you have on the left side a Bayesian network, several variables denoted by circles here, and the arrows denoting causality. A causes B, B causes C, like that. And so this illustrates some kind of a physical causality. One action causes another action and so on. Maybe it's a robot arm that is got some causality built into it. And then here we have a standard deep neural network with 4 layers and some representations which are used for downstream tasks and so on. So it's some combination of in this case, a neuro on this side, a neuro side, and this is a symbolic side. It's a neuro-symbolic AI. So our goal in these few lectures is not so much on the neuro side of things, but just on the symbolic side. It's a hard problem, and what can we understand about it? Here is an example of causality in computer vision. And here we have a picture of a baseball player. So let's see if we click on it, if that works. Okay, let's see if we can watch it. This baseball player is swinging his bat. And as he swings the arm, the bat moves. So there's a causality between his arms and the bat. There's no correlation in that the bat is not the one that is moving his arm, right? You would agree that it's the arms that move the bat. And you see the ball comes and hits the bat and changes its direction. It is coming from right to left, and it is now going from left to right. You know, it looks like he's hit a homer here. So a good hit. So there is causality between the arms and the bat. There is causality between the ball and the bat. And we understand this. So we human beings looking at it understand that this is the case. It is the arms that cause the bat to move like that and not the other way around. So if you're trying to describe it, we know which comes first and which comes next, right? First comes the movement of the arm, then comes the the bat, and first comes the ball, and then it's the bat which causes it to return, and so on. So you see, even a simple thing like this has some causality built into it. Okay. So it's the causality, it's the player's arm that is causing the bat's movement and not the other way around. The bat is causing the sudden change in the ball's direction. There is another concept that we encounter that we deal with, human beings can deal with, is not just, so first of all, there is this probabilistic correlation, which is the simplest type of thing. Two things happen simultaneously or in the similar way. That's correlation. Causality is one causes the other. The third one is counterfactuality. What would happen if the ball flew a bit higher and didn't hit the bat? So that's called, it didn't happen. The ball hit the bat in this case. But we're asking a question, what would happen if the ball flew a bit higher? Didn't hit. So that the batsman in this case is missed hitting the ball. What would happen? Where would the ball go? And so on. So it's called a counterfactual, imagining what would it be. And these are things that human beings do. So the basic probabilistic models, for probabilistic queries, it does not matter whether the model is causal. We only care about encoding the right distribution, right? What is the probability? If there are so many possible actions, what is the probability distribution over all those actions? This is our classic joint distribution in a student Bayesian network, where we have 5 variables: difficulty, intelligence, grade, SAT score, and letter. And we have some joint probability distribution of all of these variables. And in this Bayesian network, which is a directed acyclic graph here, we have only encoded conditional distributions. Of course, when the node doesn't have any parents, it will have only marginal distribution, like difficulty is D0, D1, and intelligence is I0, I1. Grade has 2 parents, difficulty and intelligence. So we have grade can be G0, G1, and G2 corresponding to A, B, and C. And its parents can take on values I0, D0, I0, D1, and I1, D1, like that. And there are probabilities here. So this is called as a conditional probability distribution table, CPD, which tells you all about the behavior of grade given settings for the 2 binary parents, difficulty and intelligence. Similarly, SAT is based on only 1 parent here. So it's SAT score can be good or bad, and intelligence can be high or low. So there are only 4 possibilities here. And here we have letter that goes along. The letter written by the professor is good or not so good based on the grade received in the course. And we say that this Bayesian network has a bunch of CPDs, conditional probability distributions. The joint distribution of all the 5 variables written like this can be obtained as a product of these conditionals, xi given parent of xi. And so you can calculate the probability of any given setting for any of these variables using the joint distribution. And the joint distribution of this case, D, I, G, S, L are the variables. And we can say it's P of D times P of I times P of G given DI, S given I, and then L given G, right? So this is a joint distribution. We say this is a Bayesian network. What do these arrows mean? These arrows ideally would have meant some kind of causality. The way it's written is indicates causality, like intelligence indicates grade and intelligence indicates SAT, and then grade indicates letter. But one can write any Bayesian network for this set of variables as long as you capture the correct CPDs. So it need not be causal in a Bayesian network. And that Bayesian network in this discussion gets extended occasionally. It's got difficulties preceded by coherence, and then grade influences happiness, and letter influences job offer, and job offer influences happiness, and so on. Supposing we wish to infer probability of J, because this encodes the entire joint probability distribution, which is C, D, I, G, S, L, J, H, one can marginalize it over all the other variables and sum it over it, and that gives you exact distribution of P of J for each setting of the value of J. And what is this quantity here? It is just a product of all the factors. These consist of all the conditional probabilities. So this is a complete representation of a probability distribution. And these can be learned using standard techniques for Bayesian network learning, which involves once the structure is given, you go about inferring the parameters for that particular structure. But a Bayesian network is not necessarily causal. Bayesian net is only an efficient representation of a joint distribution in terms of the conditional distributions. And several different Bayesian networks can represent the same distribution. We can say it's an equivalence class. This Bayesian network is equivalent to the other one. And when you evaluate every one of them, I guess it depends on the kinds of connections you give. It makes different assumptions, but they all represent the joint probability distribution. The conventional wisdom is that a good Bayesian network should correspond to causality. An edge x arrow y suggests that x causes y either directly or indirectly. And why should we prefer a causal Bayesian network as opposed to some other Bayesian network is that the causal Bayesian networks tend to be sparser and more natural. So, view of imposing causal semantics. A type of reasoning in which causal interpretation of the network is critical. Okay, so where is it critical? Will an intervention where prevent smoking in all public spaces is likely to decrease the frequency of lung cancer? So if you have a network, look at this one here. This is a causal Bayesian network. Age influences exposure to toxics and smoking. Gender influences smoking, and exposure to toxics and smoking influences cancer, getting cancer. And getting cancer influences the test called serum calcium. And also the getting cancer influences whether one has lung cancer, right? So will an intervention where, so supposing we intervene and say, if we ban smoking, will that reduce to lower cancer? So in order to answer that, we need to understand causal relationships between the variables. So causality becomes important if we want to ask such intervention questions. So interpreting a causal model. Edges have a significance, and interpretation distinguishes between two networks, X arrow Y and Y arrow X, which are equivalent probabilistic models. So one can construct, if it is just probabilistic data we're talking about, we can construct Y given X, probability of Y given X for each setting of Y in each setting of X. Similarly, we can construct X given Y. And that will give you, both of them will give you the same probability answer for any setting of X and Y. You ask the question, doesn't matter which model it was. Causal models aid intervention. Causal models matter when we want an intervention. We do not simply observe the variable values, but can take actions that manipulate these values. We just talked about action is, what if we ban smoking? Effective actions. Actions can affect the world in many ways. Even a single action can have multiple effects. Our goal is to isolate the specific issue between understanding causal relationship between variables. So we're going to look at action called intervention. Conditioning and intervention. We consider ideal interventions where only a single variable is affected. So we look at this thing called ideal intervention. We say do Z gets the value. Z is the random variable, and so lowercase italic z is the particular value. So we say set that abbreviated as do of z, which forces variable to take the value z and have no other immediate effect. We forces it. When we do that, we are interested in the queries of the form P of y given. So we are saying, what if I just set this one variable? So we say smoking is set equal to 1. Then we're asking questions of the form, what is the distribution of y given? So y is another variable, such as maybe cancer. Or more generally, y given do of z x equal to x. So there are some set of variables that are given values, and we are just doing one setting and we're asking about y. These are called intervention queries. That sounds pretty trivial in sense, look, you already have the CPDs, can't you just tell me the probability when you know the value of one? But it turns out that it's not so easy. Intervention queries. A new type of conditioning if an event of the form do z equal to z corresponds to a case where an agent directly manipulated the world to set a variable z to take value with probability 1. So it's no longer that z has like 3 values or grade has 3 values, for example, but we force it to take on 1 with probability 1. We're interested in answering queries of the form P of y given to z, x equal to s, set the variables z to z, observe values of x, and wish to find the distribution of y. Well, where would this be useful? Examples of intervention queries. Diagnosis and treatment. If patient takes meds, will patient get well? Right? So we're saying probability of health given do m equal to m, in the sense if you force the patient to take the medicine, which is different from P of h equal to m1. So this is, we're saying set m equal to m1 as opposed to given m1. Patients taking meds on their own are healthier. So we are not talking about observational data that people take that, when they take the medication, are they healthy? And in this case, we're talking about a forcing an intervention. Marketing. If we lower hamburger price, will ketchup sell more, right? And hamburgers and ketchup go together, I suppose. Not a standard observational query, but one in which we intervene in the model and thereby change its behavior. We have a complex network about item prices in a grocery store. We're asking about what would happen if we did something like hamburger price is lowered. Policy making, if we lower interest rates, what gives rise to inflation? Will that, this is not be that, will that give rise to inflation? Scientific discovery, we just saw, does smoking cause cancer? When we formalize it, this is an intervention query. If we force someone to smoke, will they be more likely to get cancer? Yeah, what does it mean? Does smoking cause cancer? If someone is forced to smoke, will they be more likely to get cancer? So these are the kinds of questions we want to ask. Counterfactual queries are a different type of causal query. We already have some information about the true state of the world and want to inquire about the state of the world had we been able to intervene, all right, and set the values of certain variables. So we're saying it is not observed data, but we want to consider that. Example, would the US have joined World War II had it not been for the attack on Pearl Harbor, right? So we know that there was an attack, but we're saying, what if it did not happen? So counterfactual queries are not hypothetical history questions. Legal liability case. Did the driver's intoxicated state cause the accident? This is a kind of a legal liability case in the court they talk about. The question really means, would accident have happened had driver not been drunk? So that is a counterfactual, saying the driver was drunk. Would it have happened had the driver not been drunk? So treatment and diagnosis. We are faced with a car that does not start, right? But the lights work. Will replacing the battery make the car start, right? So in a way, we are saying it is not observed data, but we are trying to intervene in some way. So the answers to queries. So this is the whole issue. What does it take to answer such a query given a Bayesian network which is causal? Answer to an intervention query, P of y given do of z x equal to x, is quite different from the answer to the corresponding probabilistic query, P of y given z given capital X equal to x. Example is given next. Right. So this is again a version of the student network we just saw earlier on. In this network, we have difficulty and intelligence influence grade, and grade influences job. Intelligence influences SAT, and SAT also influences job. So we have a Bayesian network. Hopefully, it's a causal Bayesian network. And we have difficulty D0, D1 probabilities are there, 0.6, 0.4. Intelligence I0, I1, high low intelligence, high intelligence, maybe 0.7, 0.3. And then the grade has three values, G1, G2, G3, and corresponding to grades A, B, C. And the probability of I0, D0, I0, D0. And I1, D1 would be, I suppose, I1 means high intelligence, and then D1 is low difficulty. In this case, the probability of grade A is high, 0.5, right? Grade A. I1, D0. I1 means high intelligence, and D0 means it is not so difficult. Or maybe that is a difficult case. It is 0.9, okay? So not so difficult and very intelligence means 0.9 we got here. Anyway, these are all the, this is the table here. Similarly, SAT takes on S0, S1, and then I0, I1 are the probabilities associated with intelligence. Okay, we say that several correlations exist in the student Bayesian network. So the issue we're interested in, can we distinguish between correlation and causation using these probabilistic graphical models of probability distribution? Now, correlations exist between grade and conditioning on grade of A. Supposing we say grade is A, correlation increases probabilities of high I. So grade is correlated with I. Grade is also correlated with SAT. And grade is also correlated with job. So there are all kinds of correlations that exist in this data. So if you're interested in P of I1, G1, which is intelligence given grade. Supposing you say grade is A, student has received a grade of A. Can you calculate the probability of intelligence? The other way around. You can do that because we have a joint probability distribution. We can do all kinds of marginalizations to obtain whatever probability we're interested in, I1, G1. Similarly, so given the grade, one can get, grade is A, one can determine the intelligence. Given the grade is A, one can determine what might be the SAT score. That is S1 given G1. And J1, that is given a high grade, what is the probability of getting a job, right? All of these. And can be obtained from the joint probability distribution with I1 given G1 greater than I1 given G2. So the intelligence is higher if the probability of intelligence is higher if the grade is A rather than a B. And similarly, the grade is an A. The SAT score has a higher probability with the grade probability S1, particular SAT score, higher probability with a better grade, and so on. Similarly, job also. If we set grade to A, we expect, right? Okay, I was just checking to see whether there were any questions, comments. Okay. All right, so let's go back to yeah, here we go. So if we set grade to A, we expect probability of J, job given grade A is equal to probability of J. So if we do this action, we expect this probability to be the same. That is P of J1 given to G1 equal to J1, J0. So J can have J0 and J1 values. So those follow. By doing this, it uses the same values as we have from the conditional probability table. What about probabilities associated with intelligence and SAT? Our beliefs don't change of I1. Supposing we say we force the grade to A, It changes the probability for job, but it does not change the probability for intelligence. It does not change the probability for SAT. This analogy is given as, supposing the student hacked into the system and changed the grade to A. Will the student have a higher probability of getting a job? Well, it depends on what was the probability of getting a job with an A grade. So it's the same probability. What about the probability of intelligence? Does that change? Well, there is no causality here. Similarly, grade doesn't influence the change in SAT probability distribution. All right, so this has been forced here. The rest of the world remains the same. And so we argue that while there are strong correlations between GIS and job, the relationship between grade and job is causal. And manipulating the grade does not change intelligence, does not change SAT. So we say this is an example that there are three types of correlation in this graph. GJ, G causes J is causality. GI is correlated. Why is it correlated? Because it's opposite of causality, I and G, but it's not causality, opposite of causality. And G and S are correlated, but it's not causal. It's only joint dependence. Joint depends on G and S on I, right? So that's what we are looking at here. So G and S are jointly dependent on I. So this tries to explain the difference between causality and correlation within a probabilistic graphical model that is a causal model. And one can discover whether there is causality by doing an intervention in something, one of these variables, that is this part, do of G1. And then that did not change job, which means that is causal. So the causal dependence remains the same, but the correlations are as before, right? The correlations exist, but in this case, so for example, I1 given do G1 is not the same as I1 given G1, right? Given G1. So that is not the same. It's just I1 itself, right? Intelligence itself. The prior probability here, and it's not I1 given G1. Whereas here it's J1 given G1. So these ones behave differently compared to the other one. So the goal of a causal framework is to provide a rigorous basis for answering queries involving intervention. So the whole crux of the matter is, can you perform interventions and discover causality? Allow us to distinguish between three cases: causality, opposite of causality, and joint dependence. Can be used to answer both intervention and counterfactual queries. Counterfactual queries require much finer grained information, which is difficult to acquire in practice. So correlation between X and Y can arise in multiple settings: when X causes Y, when Y causes X, when X and Y are both effects of a single cause. Leads to question of identifiability of causal models. If we observe two correlated variables, what can we infer about the causal relationship between them? So relationship between events, okay, here is event A and event B, which are independent, nothing to do with each other. A causes B is this graph, A causes B. B causes A is this graph, B points to A. And then we have common causes for A and B, which do not cause each other. So A and B do not cause each other, but there is some common cause. And what kind of an example is that? A is ice cream sales, and B is drowning deaths, right? And we observe that when ice cream sales go up, drowning deaths are also going up. Well, there's a common hidden reason. It's the hot summer. During the hot summer, both ice cream sales and drowning deaths go up. It's not that eating more ice cream causes death, or death somehow influences ice cream sales. That's not the case. There is a hidden variable. That is what's making A and B correlated, right? So there are these three cases. The correlation is a broader concept than causation, in that this is causation, this is opposite of causation, this is a hidden variable. And so all of them have correlation, but not causation. The difficulty of identifying causality is due to latent factors. Identifying causality is complicated by many reasons for correlation between X and Y. When a variable W causally affects X and Y, we observe a correlation between them. So, right, W is influencing both of them. If we know existence of W, can observe it. So if we happen to know that, like, in the case of summer, right? If we know that the existence of that variable, whether it's summer or not, we can observe it, we can disentangle correlation of X and Y induced by W and compute residual correlation between X and Y attributed to a direct causal relationship. So we can somehow factor that out. There are many unobserved latent variables, and the latent variables induce correlations that do not correspond to causal relations. So in reality, we don't know what is the causality, what is the variable, latent variable that is causing the correlation. And we refer to such things as confounding factors. Confounding factors are what is making these variables look like one is affecting the other. Example of latent variable, one more example here, correlation between peptide and stomach ulcer. Because taking peptide precedes ulcer, we may conclude that peptide causes ulcer. But there's an alternative explanation. Correlation is due to a latent common cause, right? And which is pre-ulcer discomfort. Even if we account for this, there may be many other latent variables such as stress. So we're saying these confounding factors can be many, and the correlation may be due to some identifiable confounding factor, but others we just don't know. Confounding factors that induce non-causal correlation between variables are latent variables. We just saw an example of peptide and pre-existing ulcers. Latent variables, and selection bias is another one, and mixture of different populations. Example of selection bias. It's kind of very interesting to see how we can have a correlation between variables for no good reason, some latent variable. In an alumni survey, so the university sent out a survey to the alumni about what they liked when they were students at the university. And they found a negative correlation between participation in athletics A and GPA G. All right. So they found that those who participated in athletics had a lower GPA, and those who had a higher GPA participated less in athletics. So can we conclude A reduces G, or that high G tends to not participate in A? So you're seeing this between athletics and GPA. So we say if you participate in athletics, you reduce your grade, or if you get high grades, it means you tend not to participate. Well, that need not be the case. This could be a confounding factor. Alternative explanation is survey respondents S equal to S1 are unrepresentative. This can happen. Students with good A and G respond and not otherwise. So the only people answering the alumni survey were those who had either good A or good G. So we have a causal link between A and S. S is the variable about survey, how many participants were there in the survey. So it is influenced by A, influenced by G. It's what's called as a case of intercausal reasoning. In a particular setting, A is A1 given S1. Is greater than A1 given G1 and S1. All right, so two variables pointing to S is the difficult case where we have A1 given S1 is greater than A1 given G1 and S1, right? So without accounting for bias in a population, we may falsely explain correlation as causation. So in this case, is a little bit more complicated. Intercausal reasoning comes into play here. But again, correlation is being falsely explained as causation. Another example, there are several examples of confounding factors. Example of mixture of populations. Girls develop verbal abilities earlier. Boys tend to be taller at the same age. No known correlation between height and verbal ability. Say, all right, are taller people a lower verbal ability? Is that true? But girls develop verbal abilities first and boys tend to be taller. If we measure across all children, boys and girls, we see a negative correlation between verbal ability and height. Oh, wow. As height goes up, the verbal ability is less in all the children together. Here we have a latent variable of gender, which confounds the common cause. So this says there is a third variable here. It's a latent variable, gender, and that ought to be accounted for. And so it is not a case of causation, but it's just correlation. So correlations can be so widespread. Or here is one more example of two time series. Data over past century of the world says average height of adult world population in that year, H is the height, increasing due to nutrition. And the total size of polar caps in that year, right, size S, decreasing due to global warming. So you have this data, H and S, for each year. So the adult world population is increasing, right? The height is increasing. People are, because better nutrition and people are becoming taller. And the size of the polar caps has been decreasing, S. So you can say, oh, wow, somehow the height and the height of human beings and the size of the polar caps have a negative correlation. But we cannot conclude that size of polar caps causally influences population height. So we cannot simply say there is causation here, right? Also a case of latent variable, time. In this case, is a latent variable, which is over time. So that can be factored in. Nutrition, of course, is another one. So challenge of causal modeling is correlation between a pair of variables X and Y may be a consequence of multiple mechanisms. Some are causal, others not. So when you have two variables correlated with each other, that could be due to multiple mechanisms, some causal, others not. To answer a causal query regarding an intervention and X, we need to disentangle the different mechanisms to isolate the correlation due to the causal effect of X on Y. Right. So what would happen if we change X? That's the intervention. So a causal model definition. So we have talked about Bayesian networks. We have talked about the importance of correlation and causation. Now we are talking more formally about causal model definition. A causal model takes the same form as a Bayesian network. It's a directed acyclic graph over random variables. And each variable X is governed by a causal mechanism. It means you have a Bayesian network where all the connections are causal. Like in the student network that we had, it kind of was causal. And value of X is a stochastic function of the parent values. And the difference is in the interpretation of the edges. So we interpret the edges as causal. Causal mechanism CPD. So the CPD has the same form as a standard CPD, that is a conditional probability distribution. For node X and its parents U, a causal model has a stochastic function from the values of U to the values of X's parents, or its direct causes, right? So we have a CPD like we have seen before. Causality flows in the direction of the edges, so that excess values are actually determined by the stochastic function implied by excess CPD. All right, so this is just standard Bayesian network terminology. Now comes causal models and intervention queries. Forms basis of intervention queries. So intervene at X, setting to X, small x means replace excess CBD with a capital X equal to small x with probability 1. When we intervene at a variable x, setting its value to small x, we replace the original causal mechanism with one that dictates it to take the value small x. Right? So a causal model can answer intervention queries using the appropriate mutilated network. So we somehow are going to take the network and we're going to mutilate it, change it. And then we can use that to use the standard inference methods. But when we do intervention, we are changing the network. So example of mutilated network. So this is the network with difficulty, intelligence, SAT, grade, and job. Mutilated student network with intervention at G. We're changing the grade to A. It's no longer A, B, C with certain probabilities. We're just saying set it to particular value, probability 1. This is an expanded student network with arc S to J. So we have an arc S to J also here. Mutilated expanded network with intervention at G. So in this case, so you see what is happening here is this is the expanded network. This is the mutilated network. The point here is when you mutilate a network, there is no arrows coming from difficulty and intelligence to grade. Grade is set to a certain value indicated by the double circle here. These are all the same. So we are going to change the CPD here with only one value, probability being 1. No longer whatever the CPDs were in the earlier network. We eliminate all incoming edges into each variable Zi belonging to Z. That's where we are doing the mutilation or the intervention, and set it value to Zi with probability 1. So this is an example of mutilated network. Mutilated networks based on causal model. We eliminate all incoming edges into each variable, set value to 1. We just saw that. For example, we have the original network, which is slightly different without the job here. And we are converting it into a mutilated network, capital Z equal to Z, where grade becomes G1, G2, G3, probability 0, 1, 0. There is no connections between difficulty and intelligence. So this CPD got changed from that, but the others still remain the same. The others still remain the same here and same. Okay, this one is, I guess they're setting it like that. It's not, oh, okay, in this case, we are saying, what if I set intelligence? There's an intervention here also going on. We're changing it to 0, 1. Previously, it was 0.7, 0.3 to 0, 1. So we are changing it by 2 variables. A causal model C over X is a BN that can answer probabilistic queries. The usual probabilistic queries are, what is the probability of letter given grade is equal to C? What is the probability of letter given intelligence equal to I1? Those kinds of queries can all be answered here. So a causal model can still answer these kinds of probabilistic queries, except these will be slightly different. But it can also do intervention queries, such as POI do Z as follows. And we basically change the network C to see if this is called the mutilated network. And in the mutilated network, what's the probability of Y given X? So that's the kind of question we can answer. So the inference with mutilated networks. So this is C of G equal to G1. All right. And this is a version of the network. Prior over the SAT, that is this SAT remains the same and unchanged. PFS given do G equal to G2. So what we are doing is we are setting the grade to some other value, G1, G2. And so the probability SAT doesn't change when we set this up here. So probability of letter is given GFG2, right? In general, answer to an intervention query differs from an answer to some observational query. Observational query was from this data set. Intervention query is in general not going to be the same. And for instance, on other variables for sure, on S, okay? So when we come up with an intervention here, S, even though we made this change, the probability of S remains the same, remains unchanged. Right. So we observe what happens between correlated variables when an intervention occurs. Now, this also is helpful to answer some peculiar statistical questions, such as Simpsons Paradox. Simpsons Paradox has to do with classes and subclasses. In US House of Representatives Civil Rights Act 1964, 61% of Democrats voted for the Civil Rights Act, 80% of Republicans voted for Civil Rights Act. We might conclude that being R rather than D was a factor in voting for the act. Picture changes if we include additional factor, whether legislator is from north or southern state. If include extra factor, situation reverses in both north and south. The breakdown is north, D was 94% and R was 85%. And so those are the numbers here. And in the south, D was 7% and R was 0%. Overall, D is 61%, which is this number, and R is 80%. What happened? We get these numbers in one way with the overall population, but when we break it down into the north and south, in both the north and the south, D had a higher proportion, 94 versus 85, and south 7% versus 0. It's called a paradox. Simpsons Paradox is, in this case, you can say it's an unbalanced data set, but it is more general than that. And this causal framework we just talked about can actually help resolve Simpsons Paradox. Oh, wow. So there is a certain power to this intervention to solve certain correlational issues in data. So this one is about an example where we have a cure and there's a drug for the cure. Take the drug or not take the drug, cure or not cure. So this is a binary variable cure, binary variable drug. Gender is also a binary variable, male or female. And the general network says P of C1 given D1, cure given drug is greater than cure given not drug. Okay. It says 57.5% greater than 50%. So this seems to say that for the entire population, if you take the drug, you are better off than not taking the drug, 57.5 to 50. But if we now look at the male population and female population, cure given drug male. This is a cure given, not given drug male is 70% less than 80%. So cure given drug gender female is less than cure given not drug gender female, 20% of all. What happened? If you look at the males, not giving drug is better. If you look at the females, not given drug is better. If you look at both females and males together, giving drug is better than not giving drug. So this is a Simpsons paradox happening. What is happening here? So this is a mutilated. So this says if you use this idea of mutilated network for answering P of C1 given to D1, right? C1 given to D1, where we are setting this drug. The appropriate query we need to answer in determining whether to prescribe the drug or not is P of C1 given D1, but not this, but C1 given do D1. All right. So you want to take the influence out. So that is the query to be asked. So even if the two populations were the same, in this case, the two populations apparently were not the same. Even if the two populations were the same, male and female, 50-50, balanced data set, still you're going to have this contradiction. That is because of an influence of a variable that is a confounding factor, and the way to deal with it is to have an intervention that, given the drug, right, rather than probabilistically use that the drug was as admitted based on the gender and so on. Wow, it's a kind of an involved topic, heavy topic, important topic. Structural causal identifiability. Intervention queries can be answered with a fully specified causal model. Cannot fully specify causal model to presence of a latent variable. Okay, so if you are going to be using a causal network, it fully specifies all the variables, then you can answer intervention queries and get the right answers. But always there are going to be latent variables. So determining probability of y given do of x. So what does it take to answer? This is the main question is, it is an inference problem. Probability y given do of x. Consider a pair xy with observed correlation. X and y are correlated. Our task is to determine p of y given do of x, right? Set some value. Assume that x temporally precedes y, it comes before. Therefore, y cannot cause x. So we have x comes before, y comes after. We have three cases. If some correlation is due to a hidden cause, cannot determine how much effect perturbing x will have on y. All right, if some of the correlation is due to a hidden cause, let's say z. If all correlation is due to the causal link, then y given do of x is equal to probability y given x. So if all of the correlation is due to that, it directly determined. If all of the correlation is due to the hidden common cause, then p of y do of x is equal to p of y itself. So all of the correlation is due to a hidden common cause. All right, so hidden common cause, what could it be? X is a ice cream sales, Y is drowning deaths, and Z is hot summer. It's a common cause. Then all of the correlation between X and Y is due to Z, right? So in this case, Y given do of X will remain probability of Y, right? So it's not like X doesn't influence it. In general, any distribution between the two is possible. So causality from observed correlations. In cases involving latent variables, we can sometimes answer causal questions using observed correlations alone. So what it is saying is, in certain scenarios, I can tell you the causality exists in this way by only using observed correlations, but in other cases, we cannot. Identifying as to which intervention questions can be answered with observed conditional probabilities alone, and reduce the answer to a query involving such probabilities. So this is a computational issue now. So we talk about an augmented causal model. So it says if you have a causal network and you have a query, then replace one query with an equivalent one, and may be able to replace the intervention queries with purely observational ones. So the interventional queries become observational query. An augmented causal model, curly G, dagger, encodes possible effects of intervention in the model. And we view intervention as a new decision variable Z hat that determines whether we intervene at Z, and if so, what value it is. So there are a whole bunch of query simplification rules. Let C be a causal model over graph G. Then P of Y do Z, X equal to X, W equal to W is equal to do. Right? The query simplification rules, then it is the same as this. If W is d-separated from Y, given Zx in the graph GC. So this is a particular graph we construct where the query is on Z, and it's a mutilated network corresponding to that. And if W is d-separated, this gets into an idea of d-separation from Bayesian networks. Similarly, if Y is d-separated from X hat, Y is D separated from X hat. So there are all these nice query simplification rules. And now we look at what's called an augmented model, which is the basic network here, and the query of the form P of S given do of G, taking Y equal to S and X equal to G and ZW equal to phi. Augmented model G contains the new decision parent. Anyway, this is a small aside on augmented model for the calculation that is needed. Let's move on to, again, the basic question. It's a very interesting problem. This actually happened in history. So in the 1960s, they found a lot of data, and the issue came up as, does smoking cause cancer? This was a big national issue. And looking at the data, there were two competing models. One, the Surgeon General of the United States stated that there is correlation between smoking and cancer. And not only that, it's not just correlation, it is causal. Smoking causes cancer. What they meant by that was, if we ban smoking, so no smoking, then the cancer rate will be the same as for non-smokers, right? So the cancer, for whatever be the cancer rate for non-smokers, then if we ban smoking, it will be the same. And that the correlation is causal, that if you increase smoking, if a person takes up smoking, probability of cancer goes up. Well, the tobacco industry, which was invested in a very big way, a lot of America's history, the early history of America, the United States, is built on tobacco, right? When the explorers first came into Jamestown, they found nothing in the United States that they could take back to England. There was nothing of value. There was no gold, and there was no tea or nothing of value. And eventually they managed to find tobacco in the West Indies, in the Caribbean. And they said, let's try planting it in Virginia, where Jamestown is located. And they planted the tobacco there, and it turned out it grew extremely well. So they were able to take back tobacco to Britain. And so America's original economy was based on tobacco. Later on, other things like cotton and so on, right? Anyway, so tobacco was a very big industry in the US. The tobacco industry employed some statisticians who said, well, who says there is causality between smoking and cancer? And said there is no causality. And you are seeing correlation between smoking and cancer? That's because the causal network is like this, that there's a certain genotype, all right? An unobserved genotype, that is some kind of a genomic predisposition, produces craving for nicotine. So there are people who get cancer, and there are people who have a craving for nicotine. And so there is correlation between these two, and it is not this model, but this other model. Okay, so we have two groups of statisticians, one saying correlation is causal, the other one is saying it's only correlation, no causality. Both models express the same distribution over smoking and cancer. No way to distinguish them based on observed data. So you got the data about smoking, about cancer, when they are correlated. When one goes up, the other goes up. When this goes down, the other one goes down, like that. Models, however, give rise to different answers to interventional queries. Model 1, this first model, says C1, probability of C1 given do S equal to S1. What if we say the person smokes? Well, the probability of cancer given that is whatever your original table was, P of C, that's exactly that. But it's cancer given smoking. In your data set, you can look at that. Model 2, the second model says P of C1 given do S1 is equal to simply P of C1. So this says the cancer given cancer given S equal to S1 is exactly equal to P of C1. So that whatever be the prior probability of cancer given S1 is not changed. So what these two mean is, the first one is saying, if we force people to smoke, their probability of getting cancer is the same as the probability conditioned on smoking. That's the first one. Second one says, making populations smoke or stop smoking would have no effect on rate of cancer cases. So the two teams argued in this way that they have different models, that you cannot show causality between smoking and cancer, which is kind of surprising. Well, a solution was proposed by the people putting forward the idea of Bayesian networks and causal models. Judea Pearl was one of the early people in this area. He suggested combining the two models into a single one. You take the smoking causes cancer and plus genotype causes smoking cancer to give another network. Genotype causes smoking, genotype causes cancer, and smoking causes cancer. If supposing you take this network, you cannot parameterize it based on observations. You can't give all the CPDs based on the data, since both original models can perfectly explain the data. And we don't know the genotype anyhow. If we refine the model by introducing additional assumptions, we can provide such estimates. So Judea Pearl suggested that this model, if it is in this form, it is not enough. We need to kind of make some additional assumptions. One was that the effect of smoking on cancer is not a direct one, but occurs via tar deposits in the lungs. So they said genotype to smoking, genotype to cancer, and he introduced this idea of tar here. Smoking creates tar in the lungs, and tar in the lungs is what causes cancer. If you can measure tar amounts, so we need one more observation, other than asking how many people smoked, how many people got cancer. We also have to see how many people got tar in their lungs by looking at X-rays or something. And if we measure tar amounts, we can now determine probability of intervention query, C1 given do S1. All right, C1, that's cancer given do S1. Using observed correlations alone, we can calculate that based on the observation. So we are not actually physically doing the intervention, but we are asking the model. So the answer to the cancer intervention query, goal is to answer C1 given to S1, an interventional query. So we have mutilated networks. So this is the expanded network. We bring in tar. These S hat and T hat comes from this augmented network we talked about earlier. And we now have a mutilation here. What if we forced a person to smoke? Then this direct arrow goes away. And to calculate probability of C, cancer given do S1, this is the usual probability rule, marginalization, that involves T given do S1. All right, so we need to involve tar given S1. So tar given do of S is PTFS. So we evaluate all of this, and it turns out eventually we get cancer given tar do of T, cancer given do of X, gives you an expression which now can be calculated from the observed data. Oh, wow. So Judea Pearl showed that actually one can calculate the cancer given the intervention and presumably show that it is actually cancer that causes, I mean, it is smoking that causes cancer, okay? So models where P, Y, do of X is identifiable. So there's certain models, if they have this nature, X to Y, X to Z, Z to Y, and there is some bidirectionality here. The bidirectional dashed arrows indicate cases where a latent variable affects both of the linked variables, affects both of these linked variables. So models where P or Y given a do of X is identifiable. In this case, we can actually get the value and then determine for ourselves whether this is causality or not. And this particular case, we had smoking tar cancer. The smoking model has the same form as the D. It has this form: smoking, tar, cancer. And the genotype is this. Right? So that is the same type of model. So certain types of causal structures lend themselves to interventional queries and others do not. Models where P of Y given dou of X is unidentifiable. Right? Certain structures, you cannot use it to determine, to evaluate the interventional query answer, which is what tells us whether it's causality or not. Okay, this is again summarizing that it's a three-level causal hierarchy. We have association, P of Y given X. This is a standard deep learning. This is what it does. Right? What is, like, predicting what is the class and things like that. Intervention is do of X type of thing, doing and intervening. So this involves a different type of reasoning. It cannot be answered in every case, but in certain cases we can. What if I take aspirin? Will my headache be cured? What if we ban cigarettes? These kinds of questions here. Counterfactuals are imagining and retrospection. Why? So these are what is questions are what deep learning networks do today. What if is possible if we program interventions and causality, and why is counterfactuals. And that's the most involved of these, and not easy to answer some of these kinds of questions. So to summarize, we have talked about how to determine causality, that mud is caused by rain, or rain causes mud, or rather than mud causes rain, or rain causes umbrellas to be open, but if you open umbrellas, it doesn't start raining. These all sound like common sense kinds of questions for human beings. Or in the baseball bat, right? It's the arm that's driving the bat and not the bat that is driving the arm. Again, we know this basic functionality of causality, which comes first and which comes next. How do we get deep learning networks to be more sophisticated than simply to say that movement of the arm is correlated with movement of the bat, or mud is correlated with rain? That is not enough for us. We want to have the causality so that it can be used to be more intelligent in its answers and its reactions and so on. That's a challenge. So we have more to study in causality, and then we also will look at some of the work done by Benji and others on bringing deep learning networks to perform things like interventions and so on. Okay. All right, we'll stop at this point today.